Hey guys, welcome back. Today I want to talk about drag acting on an airfoil in subsonic speed. The reason why I emphasize the fact that it's in subsonic speed is because drag is very related to speed, aka the Mach number. Now, Mach number is simply the velocity of the airplane over the speed of sound. We denote speed of sound as a, and if the velocity of the airplane is the same as speed of sound, it would be 1, which we call it the sonic, right? So there's usually 4 different kind of Mach regions: the subsonic region, the transonic region, the supersonic region, and we have the hypersonic region. Now, the subsonic region is usually 0.3 Mach. Transonic is usually 0.8 to 1.2, and supersonic is usually 1 or 1.2 to like 3 or 5, and then hypersonic is that and above. Now, we're talking about subsonic today, and there are some assumptions. We assume that it's incompressible. The reason why we assume it's incompressible is because the compressibility of the air in this speed, in 0.3 times the speed of sound, I will erase this Mach. It compresses the air a little bit, but it's very small, it's very minute, so it's negligible. So we neglect it and we assume the air did not compress at all. Okay, so for drag, there are 2 types of drags. There is the friction drag and there is the pressure drag. Pressure dot. Now, friction drag, we all know that it's just a net shear stress, right? But for pressure drag, we're not really familiar with pressure drag because we didn't really see it. We're not really familiar with it. Well, pressure drag is simply a net imbalance of pressure acting towards the drag direction. There is imbalances of pressure, and it could be acting in different kind of directions. It could be acting in the lift direction, it could be acting in the drag direction, maybe the weight direction, maybe the thrust direction. However, we only consider it pressure drag if the imbalance of pressure is acting towards the drag direction. So let's do an example. We have an airfoil here, since we're talking about an airfoil, and let's say like this region right here is A, and this region right here is B. And let's say the pressure at A is about 10 kilopascals, and the pressure at B is 5 kilopascals. Well, we all know that pressure moves from high pressure to low pressure, so there's going to be a net imbalance pressure acting from left to right. And as we see, the force from left to right is at the drag direction, right? Up is lift, to the right is drag, and this is obviously the drag direction. So since we know that, we'll move on. So we can just add them together. Friction drag, friction D, plus pressure D equals total D. Now, in the aerospace engineering world, we don't use total D. We use another word. We use profile drag. Now, don't complain to me, I didn't invent this word. And for friction drag, we make it a little more specific and we say it's a skin friction drag. And for pressure drag, we usually can write just pressure drag, but we can be a little more specific and we can say it's pressure drag due to flow separation. And you might be asking, okay, so how come there's flow separation? Well, flow separation is actually what makes the pressure change. So there's this thing called the boundary layer. and it's actually a very thin layer of airflow near the airfoil. And you know, it's best for it to remain attached. However, due to viscosity, at some point in the airfoil, the boundary layer detaches. So we have an airfoil here, and then a very thin airflow layer of airflow on the airfoil surface. But due to viscosity, if there's no viscosity, then the boundary layer will not detach. However, in nature, air have some kind of viscosity, so the boundary layer does detach, and then, you know, it could be move on to turbulent layer, and then it might create some eddies and stuff. Now, due to this, there's some change in pressure in these regions. Therefore, there is an imbalance of pressure acting towards drag direction. Now, this is what makes what creates pressure drag. And now, just like anything else in the aerospace engineering world, we describe this in coefficients. Let me clear this page. Let me go back to white, and then skin friction we denote it as C subscript F plus drag due to pressure, which we denote it as D comma P, or, you know, you can probably just write CP, equals to total drag coefficient, which is just CD. So today we learned about this. This friction drag is caused by net shear stress. This is caused by flow separation because the boundary layer separates due to viscosity, and that causes a change in pressure. And because there's change in pressure, there's imbalance in pressure. And if that imbalance pressure causes a force in the drag direction, that is the pressure drag. And if we add them together, this is our total profile drag of the airfoil. And remember, this is the airfoil. This is not three-dimensional wing drag. For that, I'm going to be talking about that in the next video. So I'll see you guys in the next video. Thanks for watching this video, and I'll see you guys later.